Welcome everybody. I'm John Laker, Director of Marlow Energy Group. I'm hosting the event today, and we have with us Tom Gregory, who will be talking about air leakage. I'm not going to give him a great introduction. He can tell us, hopefully, all the interesting things he's been up to and what he's qualified for. But if I can hand it over to him. After he's finished, there'll be a question and answer session. So save your questions and answers up. I don't think we'll bother using the chat. There's only 9 people present at the moment. I'm sure we can handle that by people just raising their hands. Okay, over to you, Tom.
Thank you, John. I won't go into a great deal of history about myself, but my name's Tom Gregory. We've got a company called Air Leakage Testing, which sort of says what it does on the tin. We also do sound testing and vent testing, but primarily our business is air testing. I've been involved in that area on and off for about 20 years. Originally, I was involved in testing and setting this up at the Timber Research and Development Association in Hewenden, and sort of developed the business there, and then went on to set up my own version of it. So I will skip through some bits and pieces. I'll go through it fairly quickly, but we can obviously revisit things or pick up things within questions. The plan such it is, just a little bit about air tightness, but you guys are probably fairly informed on that already. I'll just touch briefly on the wider picture in terms of requirements, which is mostly for new buildings, but there are things coming through that are going to affect more in terms of the existing stuff. Just quickly on the principles of the testing, and then probably we'll spend most time is actually talking about where we see the leakage coming from, the sorts of things to look for, and the things you can do to resolve it, and then the questions, as John mentioned. Air tightness, air leakage, air permeability, whatever you want to call it, essentially is basically the heated air from our houses or other buildings escaping through gaps, cracks, places it shouldn't, and the cold air coming the other way, and obviously then having to heat that air again, and therefore has got a significant impact on energy consumption. It's sort of part of what they sort of dubbed the sort of fabric first approach. So when we're talking particularly to sort of from a new point of view in terms of what people might be looking to do, it's trying to understand that essentially if the building fabric isn't right in terms of the thermal performance and the lack of drafts, essentially, then other features, air source heat pumps, photovoltaics, other things, you're not going to get the maximum efficiency. MVHR, for example, you put that in and the air tightness is there, then a lot of your heated air is going to be bypassing the MVHR system in terms of what it's doing. It also is important mentioning ventilation, that there has to be a balance. So we'll come to the numbers and some of what that means in a bit. But obviously buildings should breathe, should be some ventilation in terms of what we're doing. And it's getting the balance right. So if the house is designed to be airtight, then it needs something like an MVHR system, something sophisticated and relatively, whole house in terms of providing ventilation. The houses that we're testing day in, day out, and sort of middling kind of air tightness, then, a few extract fans and some trickle vents used properly is an appropriate balance. But what you don't want is to have a super airtight house and no ventilation, and obviously the opposite, overly ventilated and no air tightness. So this isn't so relevant for you guys, but just to kind of in terms of what's going on in the wider world in terms of air tightness testing. So air tightness has been a requirement for probably about as long as I've been involved in it. So I think 2006 it started to kind of be sort of more day to day in terms of all new buildings. Essentially, used to be able to do samples when you had like a few houses or a block of flats. That's no longer the case. They've also recently dropped the overall requirement, but essentially we will come to the numbers the same. We'll kind of give that some context in a minute. But basically, pretty much any new building that's built at the moment, with very few exceptions, now has to do an air tightness test. And it's been kind of moving that way for the last sort of 18 years or so, and it kind of every time they have a reiteration, then it gets closer and closer to basically more houses, more buildings being tested and tighter requirements. It's all tied in with the SAC calculation, so the energy performance certificate. So lots of things that go into an energy performance certificate on a new build or one that's done as based on the full data information can be gleaned from either sort of laboratory testing or real world experience or calculations. But air tightness is very much linked to workmanship and quality control on site. So the only way to know what the air tightness of any specific building is to do a test. And we'll come to the process for that. The better that test is, it goes into the energy calculation, and then it can have, depending on the differences, a significant impact on the overall energy rating of the building. There's no formal requirement for existing buildings, but we're seeing much greater call for it. There are certain energy saving schemes out there. So BREEAM and WELL, which is an American scheme for commercial buildings, more often. A lot of buildings we're doing in London, like offices, even sort of 80s, 90s offices that aren't as energy efficient as their more recent counterparts. They're looking to do air testing, feed that back into their energy calculations into these schemes and try and big up their energy requirements, because otherwise they can't rent them. So we're seeing quite a lot of that on a bigger scale. On a sort of a residential scale, there's things like Enefit, which is the passive house retrofit for existing houses. And then more just so informally, where people are aware, obviously, of the impact of climate change and the cost of energy, and are looking to see what they can do in their own houses. I guess some of you guys are probably fairly, far down that road, or looking at kind of the bigger picture, and other people just to kind of, we get calls from people who are just fed up of sitting in a cold house with drafts blowing around, and they're using, the classic old sort of sausage dog kind of draft excluders just to kind of, and it ultimately comes down to, yes, there's the benefits of saving money and saving, energy, but actually just sort of comfort levels. This lady I recently did in Olney for her house, and she just basically was driving her mad. She was sitting in a cold house, drafts were going around. One of the children's bedrooms they can't use because it's so drafty. So at the extreme scale, there's a kind of a bigger picture as well. So I'd mentioned in the last slide that the maximum you can have for building regs now for new builds is a figure of 8. That's 8 meters cubed per hour per meter squared at 50 pascals. So that effectively is the amount of airflow, so meters cubed per hour, you're getting through every square meter of the external envelope, the surface area of the building, when you've got a pressure difference of 50 pascals. Okay, basically 8, 10 is a leaky. Yeah, that you wouldn't want to have an 8 or a 10 really in your house. You would notice that in terms of drafts. BRE produced a figure when this was first coming out, basically saying that a figure of 10 is equivalent to having a 20p size hole in every square meter of that external surface area of your building, your house, which is not ideal by any means. So the new requirement for building regs is an 8. So obviously the lower the number, the less air leakage, the better, up to a point. And that's still relatively leaky. What we're seeing day to day, which seems to be where the sort of new builds have kind of settled, is a sort of default figure of 5, which is kind of in that area, which means that if you can pretty much achieve that with any type of construction, with enough just basically care and attention, and making sure you don't seal off most of the kind of key areas. So it does mean that most places we go, it's like a strong smell of mastic, and there's a lot of expanding foam holding up the kitchen. But it can be done, and ultimately it is an improvement. The 5 is obviously significantly better than a 10. It's significantly better than what it might be, a few years ago when there was no care and attention to it. It might be in a 15 or a 20. So it is a significant step in the right direction. It's relatively easy to balance out with ventilation. You don't need specialist ventilation. It wasn't that long ago when, you know, people were still kind of, you know, well, people are going to suffocate, we're going to have carbon monoxide issues, the building's basically going to wither and die because we're achieving an air tightness of a 10, you know, even at a 5, you know, a few trickle vents, you know, extract fans where you expect them to be, balances the, you know, that sort of level of air tightness pretty comfortably in terms of what it's doing. We'll come back actually, and then we get right down to kind of the super duper properly airtight, these sort of passive houses and equivalent. So the requirement for passive house for new builds is 0.6 air changes. So depending on the proportions of the house, that's almost always going to be under a 1 in terms of the air permeability, the meters cubed per hour per meter squared. And that is seriously tight. So when we are doing sort of passive house or NFIT, which we've got a few on the go at the moment, you're getting to the point where you're doing preliminary tests early on. So when you're kind of trying to seal the building off at sort of first principles, and then literally when we're doing that, we're kind of blowing smoke and moving things around, and they're going and they're taping every little gap. They're using the air permeability, purple paints and various grommets and special products and things to seal every little bit and piece. Because of that level, as I say, it's close to, you know, is really as achievable and measurable, close to airtight as you can get. And as I say, part of that program is obviously getting the proper ventilation. You know, you would not want to be that airtight and just have a few trickle vents open. You know, it has to be balanced against that. So the other kind of end of the scale, for kind of depending on where it is. So for reduced data SAP, which would be what you sort of do when you're, if you're selling or renting a house for a normal basis, it's not kind of at the forefront, but in the background of those numbers, they're sort of assuming an air permeability of sort of 20, 25. In the new regs for new builds, if you can come up with circumstances that you can assume a value, then it's 15, which basically is very leaky. We'll come back to some of that again in a bit when we talk about some of the things that's happening. It's by no means the bulk of our business. You know, most of what we do is new builds, all sorts of different types of buildings, but there's an increasing interest, you know, in terms of web inquiries. You know, we get, you know, a couple a week, so not massive numbers, maybe 10 a month or something, from people, homeowners who want to look at air tightness and try and improve it. We've tested a range of houses, so, you know, 30s semis to 60s detached and all sorts of things in between, varying kind of initial scores. Actually, I know don't want to sort of kind of broad brush it too much because we've got a fairly small kind of pool of information, but we've seen surprisingly good results with, should we say, more traditional build, where we've kind of got, which is more challenging in terms of other things like insulation, but like solid masonry construction. So, you know, solid brick walls, plastered. I mean, essentially, it's simplicity is part of the thing. You know, effectively, you put a relatively impermeable layer directly over a porous layer, and there's not much else to kind of worry about. It's quite simple in terms of that. Relatively few services coming in and out. Whereas, say you test a 70s, early 80s houses where they maybe were starting to kind of not experiment, but the fairly early days in terms of dry lining going on from that, they actually tend to be quite bad. And then you've got the other extreme. I tested my old Victorian house before I lived in this house, you know, and you've got timber floors and you've got, you know, designed to be well ventilated, and you are then into the 20s in terms of what's going on. But fairly typically, when we test houses that haven't been designed with air tightness in mind, you typically are talking double figures. So 10 and above, 10, 15 is a fairly common starting point from where we get. And then obviously if you then in the final reckoning get down to a 5, that's a pretty significant improvement in all those things I mentioned: comfort, energy, etc. So the test itself, for those that haven't seen one, is a pressure test. Okay, so we test to various standards, but essentially the kit comes from America mostly, although there various places you can go get it from, but ours is all from America. And essentially, you stick a fan into normally the front door, but it could be any door, and that fan then is used to create a pressure difference. So you take into account the barometric pressure and the temperatures and other things. So it all kind of gets factored into the calculations. There's sort of constraints in terms of wind and all sorts of things. So that's all kind of taken care of. But in simple terms, effectively, we use these fans and we measure how much airflow we're having to simply say, let's say, put into the house to achieve a certain increase in pressure. And then in sort of simplistically, the amount of air that's then escaping out of gaps, cracks, drafts, etc., and maintaining that pressure is the same as we're having to supply to keep that pressure. So by measuring the amount of airflow we're putting in, it becomes a measure of the airflow that's going out, and that's basically then divided by the size of the house. So for air permeability, it's the surface area or the envelope area, and for passive house sort of air changes, it's the volume. It tends to come to a similar number on houses. And as I say, the final number from an air tightness point of view, from a building regs point of view, is meters cubed per hour per meter squared at 50 pascals. So 50 pascals isn't a great deal of difference pressure-wise, but it's probably about 10 times what you get under sort of normal conditions. So like today, when it was relatively kind of still and pleasant earlier, like in the morning, there'd be almost none. You know, you'd be in 0 point something or other moving each way in terms of the natural pressure difference. You know, a bit of wind and something that can lift up to 5-10 pascals. So 50 is quite a bit more, but obviously we can't really test it at the lower levels because a slight change in the wind and your measurements become nonsense. So what you do is you take a series of readings at increasing pressures, and effectively then you work out a relationship, and then it calculates the result of 50 pascals, and it gives you a benchmark across the industry, which they understand, you know, gets fed into energy calculations based on certain assumptions and theories in terms of what it is. So it gives, let's say, it's not in your house on a day-to-day basis. If we say that it's getting a 6, it's not what you're measuring day to day, but it's as a comparable measure against other people and an indicator of kind of how leaky it would be. So when we're doing the test, or in advance of doing a test or doing some work, we can use that pressure difference to basically work out where the air's going. It's, I don't want to undermine it, but it's not rocket science. Ultimately, it's drafts and it's holes and it's cracks and gaps and etc. So, but what we can do when we've got if we reduce the pressure in the house with our fan, then effectively the air comes in at you as a draft. And because we're 10 times the normal pressure difference, it comes in pretty obviously, and on a cold day, very obviously, in terms of where it's come from. And you can literally, as you go around, feel where the drafts are coming, not only to identify them, but compare them relatively. So that if you're getting a little wisp of air through a socket, compared with it's blowing a gale around the loft hatch, then that's obviously where your focus needs to be. So it allows you to prioritize where the bigger problems are, where the big wins can be made. You can do it the other way as well. So you can positively pressurize or increase the pressure in the house, and then you smoke to basically watch the smoke going through a little gap, or potentially be on the outside and see where the smoke is coming out. It's quite good for, you know, the beauty of the smoke is that you can take a photo or take a video, and then you can show somebody else what went on. In terms of precision, actually feeling for the airflow is probably a better way of doing it, but you can't really explain it to your builder or somebody else the next day because it's, you know, you can't really see it. You can hold a bit of paper and see it flapping about. So in terms of the kind of the fundamentals of it, you know, as I say, it's not too complicated. You know, you're talking about trying to create effectively a continuity of your air barrier. So that air barrier wants to be made up of something that isn't going to let the air through too readily. So something that isn't that porous, but it's the continuity that's important. So every time you put two parts of that together, you obviously don't want a gap. And every time you stick a hole through it for a window or a pipe, you don't want a hole around that, you know, a gap around it. So, so I've got some examples of those sorts of things coming up. If you were So for new builds or for kind of fairly involved retrofit? Yes.
Should we be seeing something?
No, you're not. Don't worry. No, we'll come to that. Oh, can you not see anything?
No.
Oh, shit. Have you not seen anything the whole time?
No.
Oh, sorry. I
It
thought
wasn't.
I must have switched it off. Can you see it now?
Yes.
All right, let's just hold on. We won't go through the words, but I'll just show you the pictures.
Well, before you do that, can I just ask, what's the difference between a bar and a Pascal?
They're different scales for the same things. So it's pressure. Don't hold me to this, but I think 1,000 pascals is a bar.
Right.
Is it? I can't remember. I'd have to check on that. But they are basically, a bar is a higher measure. So pascals is quite a small. A single pascal is a small measure of pressure essentially. So we're not talking big numbers in terms of that. So I'm trying to think what barometric pressures would be in bar. So in like the barometric pressure, so atmospheric pressure in pascals is basically about 100,000 pascals. I don't know what the atmospheric pressure would be in bar.
About thousands, I think.
There we go then. So it's maybe 100 pascals is a bar.
Okay, right, thank you.
So I don't think the photos here are too important in terms of what we went through, but there was something going on. So I'll send the slides to John as well, so you can have a PDF or a version of that in terms of the notes. So yes, this is more important. So where I was talking about the fans, that's what the setup looks like. So you've got an expanding frame that you'd fit into the front door, push the fan into it, and then you hook up various tubes and gauges and everything else to kind of then run the test. And that's how we kind of measure it and then basically calculate the final result of 50 pascals. So if you're looking at a new build or like a fairly significant retrofit, it's important to understand where your air barrier is going to be. So on new builds, there's a process they go through, kind of redlining, and they're kind of trying to trace it through and make sure in terms of achieving that continuity in terms of where it is. Obviously, in that, you want that barrier to be made up of impermeable materials. So blockwork, brickwork, etc. has got a degree of porosity. It's not going to pour through at the level, at kind of if the building's doesn't need to be that airtight. But by painting it or parging it, or ideally even plastering it rather than using plasterboard, you can seal those things off. Mineral wool. So when people try and push mineral wool into things to sort of seal it off, it won't achieve air tightness. It's better than nothing. But in terms of materials, it's going to be things like specific membranes, plasterboard, plaster, mastic sealants, the right type of expanding foams, that sort of thing, in terms of achieving air tightness. EPDMs, it's like a sort of rubbery kind of taping material. There's all sorts of specialist tapes associated with passive house as well. And then from a practical point of view, and again, it depends on kind of, probably less relevant in terms of, individual projects where people are kind of fairly intently looking at them, but on larger buildings where things can be happening kind of a little bit out of sight, out of mind, then it's important to check to make sure that in areas where it's not necessarily visible day to day, that continuity is being maintained and there aren't gaps, cracks hidden behind bath panels, under showers, behind kitchen units, that sort of thing. So some examples from fairly common things on site. So this is under a bath. So on the other side of the bath panel, you're going to have tiling and mastic seals and all very tidy from that point of view. But the bath panel is designed to come off from an inspection point of view, so it's not airtight in the bath panel itself. And then effectively, we've got an 1.5 inch gap, basically undermining any sealing that's been done on the other side of the building. In terms of that, gaps themselves. And then under a kitchen unit, something similar, where some work being done and belatedly and pushed into it, and then There's a hole carved in the corner. So again, it looks out fine outwardly, but it's worth just making sure those areas. And they're the sorts of things that turn up quite readily on existing buildings as well. When we're doing the test, those areas that aren't necessarily explored, where you go into and it's, cobwebs and dust and those sorts of things, is probably where it's going to be in terms of the air leakage. So in terms of the building being put together, or kind of working out where the junctions and joins are, these are going to be actually probably the biggest leakage paths, the most significant. So give that some context. What we're seeing day to day in terms of new builds, our most common construction is sort of traditional, so blockwork and brick with dry line plasterboard. And what that creates is sort of the dry lining, where it's dot and dab. So it's basically dabs of plaster and stuck on, and there's not a continuous ribbon of plaster sort of sealing it in. Then the air can actually get in underneath the skirting behind that plasterboard and then find its way out either through the loft or through holes in the blockwork that might be a bit bigger than what you can see on the inside. And that might mean in a house, could be the difference between sort of a 7 and 8 or kind of a 4 and a 5, because you've got that little gap over 2 or 3 floors, basically creating a significant amount of leakage. Some fairly more extreme examples where kind of fairly obvious in terms of that. Carpets going down can help, but won't actually stop it. And what we'll see sometimes is actually the air just under pressure, the carpet actually just floating. It lifts the whole carpet up, it gets under the carpet and lifts the whole carpet up. And then obviously where we stick holes in it, there's the potential for there to be air leakage. So not just less likely through doors and windows, not new ones at least. They're pretty good from an air tightness point of view. They'd be tested in a laboratory for their weather tightness. It's in the installation. So where basically they may be put in and there's gaps around the doors and windows underneath. And again, there might be a vinyl or a carpet go up to this, but that's not going to necessarily seal it, although it might, again, disguise where the leakage is. Sliding doors can potentially create, so pocket doors quite often will leak as well. There are ways and means of doing it, and there's some products I think will claim to do that, but generally it again allows the air to kind of get out of sight, beyond control a little bit, and then it will worm its way through and find its way out in some way or other. Again, most of it's just workmanship issues. Loft hatches, whether it's around where it opens or around the frame itself, common problems, and obviously pretty direct path into an unheated space. So, and also quite a noticeable draft in terms of comfort as well. Eaves cupboards, exactly the same, can be a real problem, can be quite a significant leakage path in a lot of houses. Quite often when we're doing a test, if there are loft eaves cupboards, they're going to be one of the main areas, unless the cupboard within the cupboard is actually fully boarded and sealed as part of the air barrier. If it's literally just loft space, then again that's going to be prone to it. Again, draft strips or something like that, on a loft hatch or an eaves cupboard, could make a significant difference without hopefully making it difficult to open. And then obviously everywhere you put a hole through, so soil pipes behind toilets, even the MVHR ducting, that should be, is a positive overall in terms of energy consumption, but if it's poorly fitted, then again, it allows the air to escape potentially. Boiler flues, similar things. Again, things like this, where you've got the sort of the cowl, will hide that hole, but it won't stop the air coming through. So that cowl will go on, but ultimately in terms of the air leakage, it will still just kind of move around that and be noticeable. Behind things, awkward areas, is behind a pedestal in a bathroom, so a pedestal for a sink. So not only the leakage through the hole here, but actually this gap here is effectively just going straight out, and there's no barrier here that's allowing the air to then get up behind the tiles, behind the plasterboard, and get away. So you've got a big opening there. Under a boiler, things again similar behind the bath panel. Again, aesthetically, it's not going to have any bearing on the plumber or whoever's doing it at the time. They just need their pipe to go out. The bath panel ultimately will hold that and hide that. but it obviously is going to cause a problem from an air tightness point of view. Under a kitchen, similar. They're going to be less significant themselves, but if you're going for high levels of air tightness, then, you know, around electrical fittings, you know, downlighters, sockets themselves, etc., the air can come around those. Quite a common one where you've got like a cooker hood and the kind of the covering for that, but behind here is a big hole, big square hole with a bit of flexible hosing going through it, and again, the air is going to basically pass through that fairly readily. In terms of again, electrical fittings, is an existing house. Similar thing with the pedestal, with the air getting around from behind. It's under a kitchen unit. It's a fairly extreme example in this case, but the water pipe isn't just never been kind of sealed back off again in terms of leakage going through there. So things like that where you've got, you know, again, depends on the levels you're going to or what you might be thinking about. So, you know, holes around pipework and things like that, we're seeing most commonly sealed with expanding foam, appropriate mastics. You need some flexibility in some cases in terms of sealing these things up. Obviously, where you've got linear gaps like around underskirtings and things, then mastic's going to be the way forward in terms of that. If you're looking to kind of more significant kind of levels of things, then introducing the more specialist membranes using kind of passive house kind of certified tapes and things can bring the levels down very high. We did a recent job in Oxford, which was a 30 semi, and he achieved 0.6 air changes on part of his sort of retrofit in terms of doing that. But he was obsessive. You know, really to get to that level. You know, he's thinking and sitting there night after night. He's not watching TV. He's looking around the room for where he can put his next grommet or stretcher tape or whatever he's doing. It is difficult to achieve, but you know, improvements are going to can still be significant. As I say, if the starting point was a 15, then to get to a 5 is big. Getting an extra 2 or 3 out of that, you know, is beneficial, but it's diminishing returns up to a point. You know, the effort you'd have to go from a 5 in an existing house to get to a 2.5, you know, it's going to be a lot of work, a lot more expense relatively if you're starting from a fairly easy position. Then that's where the biggest win's going to be made. So just a quick summary. So air tightness is potentially a relatively easy win. You know, and it can have a significant impact, not only just in terms of comfort, but if you were looking to kind of use that to kind of work with that number and other things that you were doing, and then have a full data SAP calculation done, then it can again have a significant impact within the SAP calculation in terms of numbers and potential energy ratings, the kind of future value. But it needs to be done in consideration with insulation. From an actual point of view, there's no point having a nice airtight house, but basically the thermal transmittance through the wall and through the windows is very high, or vice versa. You can undermine any insulation gains you have if there's lots of gaps and cracks. It basically just lets the air bypass any insulation upgrades you've made, and then that should allow you then sort of as the kind of the other factors to really maximise the benefit of heat pumps and photovoltaics and other energy efficiency measures that you might want to introduce. So what we've done for various people of late is, for those that are looking to make changes anyway, they might be as part of doing other works, whether that's energy related or just kind of more kind of improvement works generally. It gives an opportunity to kind of do an air test before that, identify where the drafts are coming from, what the degree of leakages in different areas, what things can be done about it, then factor that into the work that's being done, and then potentially, if you want to then quantify that, do an air test at the end as well. And that's the way I would advocate. There are certain easy things, and if you've literally have got a drafty door, then you can just replace a door. It's more of that. But if you're going to do work and you want to maximise improvements in air tightness, you're having insulation put in, you're doing other aspects, rewiring the house, doing other things that would kind of be fairly disruptive, then it gives an opportunity when you've got that, to get this done as well. Understand exactly what it is, where the focus should be. As I say, when we do the air testing and the diagnostics, we can point towards, right, you really want to sort the loft hatch out and not worry about this and that, save your money, focus on that, do what you want to do. And then let's say we can do some quantitative, we can do some testing on the day to try and quantify that by temporarily sealing things or closing off areas and going, well, you've got 5 leaking through your bathroom. So you'd go from a 13 to an 8. You've got another 4 going through the kitchen. So if you can address the areas there, then that's going to be a significant improvement. And then you can piecemeal do the other bits, as and when there's an opportunity to put a bit of mastic down or something. And as I say, then potentially you can then use that final air tightness result, if you did one, to then put into a full data SAP, to then not only understand it, but then from a ongoing point of view, if it's renting or selling, then that would then be taken into account going forward. Okay, apologies for no slides early on, but hopefully that made some sense. And that's me.
Thank you very much, Tom. If you can stop screen sharing, we can hopefully see a few people and take a few questions. Who has a question?
Yes, please, John and Tom. Roughly, how much would it cost, Tom?
For an air test? So air test, we typically are looking at sort of £200, £250 plus VAT, so around £300 essentially. That would include so that's the initial test, which would include the diagnostics, and then there's a short report with photos and things basically detailing that. So what we find, again, it's horses for courses, but some people, the most recent ones we've done, they're sort of working through the house, doing things on an ongoing basis, not doing the whole house in one hit. So to have a report listing things, they can kind of put, some of it to bed on the back burner, do the bits they work on at the moment, and then revisit it. So for £300, assume it's not an absolute massive house, that would cover it. If you then wanted us to come back and do the other test, that would probably be about half that, because essentially that's just doing a quick test and giving a result and confirming, hopefully, the fruit of your labours, essentially. About £300 for test and diagnostics.
Okay, right, thanks.
No problem.
Okay, next question, please.
No, Edward here. Just quick question for you, if I may. So how are you supposed to seal up all that stuff around big pipes and things? I've never found a way that really works and looks neat. It's really difficult for some of that difficult stuff to find something that molds and also seals.
Yeah, I think you're right. It's the neatness which is difficult. So a lot of the ones I showed are not on display, if that makes sense. So like behind a camera, and so it's hard to come up with an alternative, in terms of those solutions, in terms of trying to access the area where you've got something you can do fairly quickly and easily. So expanding foam is probably quite a good solution. As you say, that isn't a very neat solution. So if that's some of those where we had the boiler flue, if that's visible, if that isn't tucked away into behind something and it's like a boxing in area around it, then what we tend to see is somebody actually, they use the expanding foam, fill up the big gaps, so they kind of, so that's going through the full depth of the block or whatever, get as much expanding foam as possible, let it go off, and then they could basically saw it off to flatten it, and then basically it gets filled like literally with sort of filler, and then the final paint on it to kind of give an aesthetic thing. But it's I have to be honest, going on site it's pretty ugly in terms of what's going on. There's a lot of panicking with mastic, but they're not really kind of mastic men, and they're going around and got like the holes like this with mastic going backwards and forwards.
That's it. Yes.
Like this. It's not beautiful. If you are going back to kind of more basic, to the sort of first principles. So, for example, you're looking at it and you're going to go, right, now I'm going to strip all the plasterboard, all the plaster off the wall. I'm going to install, put some insulation in there, and I'm going to put in some membranes and seal it that way. Then you can do it obviously all very neatly. And there's grommets and tapes. I mean, there's things for everything. So there's putty pads to go behind electrical sockets. There's these like kind of rubbery kind of grommets you can poke cables through, so it seals them as they go through, like collars and things that you can put around pipes. If you can think of it, the Germans will have made some version of it for a lot of money that you can get. and do it. And then, of course, you then hide all that behind kind of some plasterboard or a final finish, or however you want to line the internal of your house, clad it or whatever, in terms of doing it. But you're right, it's difficult to get the easy win without, and make it pretty.
The soil pipes are classic, aren't they? They just, they're nice square hole, shove a big soil pipe through it.
Exactly right. Yeah, which I fully understand. But as I say when we're doing the new ones, it's one of the most noticeable ones, without kind of getting too kind of unpleasant about it. It's the one where people are going to be sitting there on a cold morning with the trousers around their ankles, and they're going to be
with a draft
coming up there from the rear, shall we say, fairly ready. And that's the one that, again, from a comfort point of view, it is a very noticeable one. And so, yeah, if you can, as I in terms of that, if you had that situation, you had the boxing and it was open at the end and it was too complicated carpentry wise to seal it, it's going to be better if you could push a mineral wool up there. It's going to be better than nothing. It's just not going to make it airtight, if that makes sense, because it's designed to breathe and let the air pass through and sort of trap the moisture within.
Yeah, I was wondering about mineral wool and just sort of sealing it all, putting some hair spray on it or something. Or
yeah, true. But yeah, exactly. Or what we see sometimes is you kind of put that in and then sort of a more mastic or foam to that makes sense. But the mineral wool is giving some substance to kind of sit upon in terms of doing it. Again, when you've got it and you've got the opportunity to just sort of shove it up and not be seen, then that's where it's kind of easiest to kind of get the benefits. As you say, trying to sculpt that sort of stuff into anything that looks pleasant is more challenging.
And suspended floors seem to be an issue as well. Tongue and groove must be a big leaky thing, and a big leaky thing around the outside where the skirting.
Yes, absolutely. Yeah, no, and to be honest, on different levels, even today where I was in new flats, ceiling voids, raised access floors, things again, it's like the bath panel on an extreme kind of basis where you've got suspended ceilings, other things that effectively allow you to have what looks like a good, aesthetic finish, but allows everybody else to kind of make a complete mess and leave big holes underneath. So similar principle, where you've got the floor and the void underneath, it's likely there's going to be some square holes around pipes going through them.
Interesting.
Can I
ask you about? Oh, sorry.
Go on, Anne.
I just wondered if it's possible to quantify the benefits of the air tightness improvements. I mean, is there cost benefits that are obvious that you maybe put into a report, or how does that work?
We sort of stopped shy of that. I think there's been work that's been done. The difficulty in terms of the specifics is that, as I say, air tightness is a contributing factor. So if you get good air tightness, but the insulation has improved, then you're not going to see the benefit of it necessarily. So I wouldn't want to. It'd be difficult to put pound, spin, and share. I can only speak from my own personal experience. So I actually live in quite a new house. So where are we now? It's 10 years old, this house. So it theoretically has got an air test certificate of a 5. When I tested it, it's an 8, which isn't desperately bad, but isn't as good as it should be. So I didn't do anything else because it's a modern house. It's well insulated from that. Well, I hope it is. It's harder to tell without getting my thermography out, but it's relatively insulated. So air tightness in my case was probably where I was losing a lot of my, from a heating point of view, at least energy wise. So I basically had a couple of days of groveling around with expanding foams in hidden places and trying to seal it off. So we basically halved it, went from an 8 to a 4. In current, when did I do that? So this is last summer. So when we had the next winter, I mean, there's obviously factors going on in terms of price changes, but I think the rates at them were fairly consistent with when I've been from the last winter before they went through the roof. I think there was a balancing act, actually, in fact, in terms of what had gone up by, but what we got from the government basically made it rates weight was about the same. But effectively, it had gone down, in our case, by about £50 in terms of we've got gas heating. Our gas has gone down by £50. But it's hard to identify as a month. But it's hard to necessarily, it might be I used the gas oven less for a bit and things. So it's harder to tell. But I think even without knowing that you know, it's not hard. You know, if you live in a house that's drafty, or with people who leave doors open a lot, or open windows and put heating on, or whatever it might be, it's not hard to imagine there's a lot of energy going out of that window, you know, or out of that draft, you know, when you're feeling it, you know, in terms of the impact of having a cold draft come in, drop the temperature, the work you're then having to, you know, the boiler's having to do to then bring the temperature back up. But as I say, you'll only see the full benefit, I think, if you sort of see it as a bit of a part of a bigger plan. You know, you're not going to do any harm by getting a bit of mastic out and sealing up some things. But the real benefit will come, I think, if you're also doing the insulation and other things as well.
Yeah, part of, as you say, part of
I think, yeah,
thing.
to see the real benefit, yeah, to see the financial, you know, significant difference.
Yeah, thanks.
Can I ask a quick question, Tom?
Okay.
There are companies around who advocate insulating under your floors. We've got wooden floors. Is that something you would think is a good idea, or is that just as much a con as the people that are insulating the inside of rafters in the loft?
Yeah, I don't. Not my area of expertise really in terms of insulation, but I'm not sure. I mean, again, I think it's a bit like the sort of law of diminishing returns, that if you've insulated everything else already, and you've sort of struck off air tightness, and you're kind of worked down that list saying, well, what can I do next? Then I suspect it features there somewhere, but it wouldn't probably, from a personal point of view, first thing I'd go out and spend my money on. You know, I'd rather probably replace the windows or do other things that, you know, feel like they would have a more significant impact. But I'm not an expert necessarily in terms of what
Okay, thank you. Any more questions?
Yeah, I've got one. Presumably, Tom, things like old open fireplaces and probably the latest thing, which is wood burners, which are always continuously open to outside, that they're quite a significant problem.
Yeah, it's a bit of I was going to say fast. That's not quite. That's a bit extreme. But the test standard basically means when you do a test. So if we test a new house and it had a fireplace, increasingly they're burners rather than open places, but there's still some. Then actually the test allows us to seal that off. So the result you get would be with the fireplace sealed off. Right. So that becomes a little bit misleading, because you say there's a clear draft there. Again, I'm not entirely sure the right terminology and things, but you're right. If you've got a fireplace, doing a mastic seal around, you know, a sink in your bathroom is going to be massively outweighed by the fact that if it's an ingle nook, that the air is going to be rushing through the fireplace on a day-to-day basis. So if you're looking to kind of do air tightness, then yeah, you'd probably have to be looking at fitting some sort of a valve's not the right word, but there's like a shutter that I've seen sort of fitted retrospectively to open fireplaces, where you can basically close it, you know, when it's not in use, and open it, and then obviously you can use it for fire, but you're not got a constant draft rushing through it when you want it to be. And obviously when you've got a fire in it, then happy days, you know, it's doing what it should be doing anyway. The burners, they're a mixed bag. So with the burners, they're quite hard to seal up, so we tend to leave them and see how they perform and then worry about it. You know, we can say we can feel the air. A lot of them, obviously the ones that cost more money, are pretty good. You kind of close a lever and it kind of seals them off pretty well. Some of them, it's a bit of a mixed bag again from building control, what they require in terms of them having like a open, like what used to be an air brick, but like a grill. That doesn't seem to be so common anymore. But some of them, they will leak. You just can't, you know, you feel it coming around the door and everything else. But they're probably relatively more manageable, so you can still get benefit from making air tightness elsewhere. But if you literally can stand in your chimney and look up and see, you kind of see the sky, then that would be something, you know, you need to do that first, really. Otherwise, you're just going to basically, you know, it's going to find the path of least resistance, and that's going to be where it's coming in anyway.
Just wondering if I can ask a question. Apologies if you covered this right at the beginning. Unfortunately I joined a bit late. But what is the sort of aim in terms of air changes? What, you know, there's presumably a building regs rate? Because I'm kind of wondering, there's obviously a balance between air tightness and indoor air pollution, and where that makes sense, where that should be at the moment.
Yeah.
Just to give some context to the numbers you've been talking about.
Yes, we did touch on it briefly. From a building regs point of view, the old regs was a maximum of 10, which is about 20 pp size hole for every square meter of your external envelope. So 10 is leaky, basically. It's now 8 as the maximum. The sort of the default value that we're seeing, kind of most people aim for in terms of new builds, and would be a good target for existing, is a 5, and that level is a good level of air tightness. So it kind of achieves that kind of goal of being, you haven't got major drafts. You've got most of the heat is staying in the building by one means or another, but you don't really need to have excess ventilation. You don't need to upgrade your ventilation by any great degree. If you're going down to sort of passive house, sort of 0.6 air changes, about 1 in terms of the numbers I'm kind of talking, then you can't, you're going to create other problems, much more significant problems in terms of air quality, if you don't marry that with an appropriate ventilation system. So the MVHR of varying types is pretty much a standard partner to kind of that sort of level of air tightness, and actually kind of vice versa, that those MVHR systems kind of work ideally at sort of around 3 and less. So if you put MVHR in a sort of an energy saving things and your air tightness is still at 15, then you're not going to see the benefit of it kind of from the other point of view. Okay. But I think, as I say, I think if you've got if you're testing your house currently, and it's you'll know yourself in terms of whether it's drafty. If it feels drafty, it probably is. So it might be sort of 13, 15. It should be relatively easy to get it to a 5, and a 5 would be comparable with a new build house in terms of air tightness, and then other things that you can then put onto that could then make it a relatively energy efficient property.
Okay, thanks.
Okay, I think we've got time for just one more question before we run out of time. Richard has put his hand up.
Can I ask, how do you actually identify where the leaks are? You go into a house. What I saw is you put a barrier on the front door and change the pressure. How then do you actually work out where the leaky points or airflow points are?
You can actually literally just feel them. So by reducing the pressure, so basically by sucking air out of the fan, it reduces the pressure. So then we've got, say, 50, 60 pascals of pressure difference lower in the house, and then the air gets effectively drawn in as drafts. And because we've got our pressure differences 10, 15 times what it would be normally, those drafts are pretty evident. So you could go, let's say it was the bathroom, literally just close the bath. So the fans are running, the pressure's low, you can close the bathroom door, and immediately, even without probably bending over, if you don't have your shoes on, but you can feel the air around the door and go, right, there's a lot coming from the bathroom. You can literally, it's rushing under the door. So then you can go into the bathroom, having know that's an area where there's a problem, and then you literally are feeling around. And if it's harder to find, your eyes are the most sensitive to that sort of stuff. But generally, the levels we're talking about, it's hard to sort of describe until you actually feel it. And most people, the first thing they say is like, I didn't think it would be that much. Do you know what I mean? And literally, the bathroom door, if there's a good amount of leakage, first of all, you probably find it quite hard to then open the door, because the air will be kind of pushing against you, and then literally go up to near to the toilet, and if there's a gap there, it'll be blowing through. But what's sometimes what you find is where you think the leaks are, or where it looks like it might be a big problem, sometimes you can see what looks like is a fairly untidy kind of seal, but there's something going on actually behind it that sealed it, and you kind of go, oh, it's not there, it's there, and that relatively small gap but over a long distance is what's causing the problem. But literally you can feel it, and as I said, you can literally compare and contrast from your own experience where the fans are running and go, okay, I've got a little bit there, but it's I'm getting showered with dust and dead wood lice or whatever. From there, that's where I want to put my focus in terms of doing it. And I'd say when we test the kind of
somebody feel then, basically, your personal or your operatives feel, so say where I can feel the flow.
Yes. Yeah, and the beauty of it is if you were doing it for your house, is that you would do it as well. So it's important, I think, that you feel it and understand kind of what's going on. We'll write it up as a report, but it's much more meaningful for you to actually literally feel it and see it, and then you'll kind of, as I say, it will help you to kind of prioritize it. And I'd say we can then quantify it to a degree. So if we've got a result of say 15 on the day, we can say, right, we know the bathroom's a problem. That's a big area. Close the door, put some low-tack tape to seal off the bottom of the door, do another test, and it's gone from a 15 to an 8, then you know there's a big win there. Rather than, I don't know, we're feeling it everywhere and it's kind of like, okay, we close the door and do it, and it's gone from a 15 to a 14.5. That would be nice to have, but that's not where we want to put your energy and time and money.
Okay. Thank you very much. I think we should perhaps draw it to a close now. But before we go, can I just remind people that we have a talk on Wednesday, the 7th of June. That's again at 7 o'clock, and this time it's on PV panels, and it's from a firm called Solability. Now, the relevance of that is that we did have a talk 2 or 3 years ago from IDDEA, who we've been recommending people should perhaps talk to, but IDDEA have subsequently gone bust last week. So consequently, Solability may be the avenue that we're looking for locally. Anyway, that's at 7 o'clock, Wednesday, the 7th of June. We've got our AGM for the members a half an hour before that, but everybody knows about that who's a member. So in conclusion, can we thank Tom for his excellent talk? Sorry, I didn't realise that you were talking about the slides that weren't there to start with. Perhaps I should have mentioned it, but I'm glad that Trevor did. But thank you once again, most interesting, most informative, and thank you everybody else for coming. It's much appreciated. Thanks for your time.